Good morning. My name is Maiullari, and today I'm going to present, also on behalf of the other authors, a study that focuses on the effectiveness of vegetation in lowering urban temperatures and on the related impacts on space cooling demand. Scenario projections in the last decades have shown that urban heat island effect and heat waves will continue to increase in magnitude and in frequency, not only in Mediterranean regions, but also in Central and Northern Europe. And this pattern is expected to affect building energy performance, in particular space cooling demand. One mitigation measure that demonstrates efficacy in reducing urban overheating is the increase of vegetation cover. However, in climatic regions characterized by strong winds, the impacts of this measure are largely understudied. Therefore, we decided to investigate the influence of vegetation both on microclimate and on building energy performance in a new district in the Netherlands. The Floriade district is being developed to host International Agricultural Expo in 2022. And after the event, the municipality of Almere has the aim to transform it in a carbon neutral residential district. As you see in the drawings, the design of Floriade Plus is shaped around the concept of the arboretum, this green orthogonal grid that is composed of over 3,000 plant species. For this case study, the goal was to assess the impact of vegetation for an extreme hot day by employing a coupling simulation method previously developed and actually also previously presented at Playa 2018 in Hong Kong. In our approach, we look at the design process not as a linear process in which the energy assessments follows the decisions on geometry, materials, and energy systems. Modeling that usually focuses on single buildings and employs statistical and average weather data, but we envision the design process as a reiterative and informed process built on integration between microclimate and energy modeling. Therefore, we use for the study an integrated method between two existing tools able to address the district scale. The two tools are MVMAT for microclimate simulations and City Energy Analyst that we use to estimate building cooling loads. The integration method is applied to compare two scenarios, the fabric for which only surface materials and buildings were modeled, and the green scenario that includes also trees and grass. The two scenarios were simulated in MVMAT, and results were used as boundary climate conditions in CA. We, of course, selected the day for the simulation, which is an extreme hot day with clear sky that reaches 34 degrees Celsius. And here we see the first results of MVMAT for a selected number of hours. What we can notice is that during the central hours of the day, temperatures tend to increase when vegetation is modeled. In particular, in the north, if you see my arrow, in the northeast area of the district. At the opposite, when we look at wind velocity, we see that the green scenarios as a generally wind speed that drops below 1 meter per second. Significant variation are also observed when comparing the scenario results to the data from the rural weather station, which is for us the base case. And the two scenarios, for the two scenarios, the average air temperatures appear higher than rural one during daytime, with a maximum difference of 1.6 degrees for the fabric scenario and 3.4 for the green scenario. While in the second graph at the right, you see a consistent decrease in local wind speed. Moreover, for the green scenario, a Spearman correlation highlighted a significant relation between wind speed and air temperature, and this suggests that in the Floriade district, the decrease in wind velocity might contribute to temperature increase. In fact, roughness elements such as trees and buildings can sensibly reduce the supply of cool air from the large water body that surrounds the district. So what are the facts in terms of cooling demand? Here, the CA results for the scenarios are again compared with a base case, a CA simulation that used data from the weather station. Over the entire day, the inclusion of microclimate boundary conditions causes an increase of cooling demand between 9.3 and 9.8%, affecting also the peaks. However, looking a bit more in detail at the single building consumption, we have noticed that the demand variation ranges between 0 and 35%, as the variability of microclimate impact on energy can depend upon also upon building typologies and position in the district. So to conclude, the urban heat island that emerged in this study is characterized by higher temperature during daytime. This pattern has been observed for both the scenarios, and average temperatures are higher when the green structure is modeled. For this particular case, vegetation has an effect on wind speed that seems to lead to a decreased supply of cool air from the lake, and also seems to overrule the cooling effect from shading and evapotranspiration. So the microclimate profile is then reflected in the results of the overall energy demand. When considering the effect of microclimate, space cooling increases of around 9.8% due to the presence of vegetation. And finally, the results suggest that further studies are necessary to assess the role of vegetation in particular in temperate and windy climates. In fact, due to the increase of overheating processes, we think that cities in the north and the central part of Europe are in urgent need of adjusting mitigation measures according to the specificity of their environmental characteristics. So I would like to thank you for joining this presentation, and I hope you enjoy the rest of the conference. Thanks, bye-bye.